of solutions. All right, we'll start with the journal. So I said a sodium chloride is soluble in a aqueous solution. So what does aqueous mean? What kind of solution? Not just a liquid, specifically a what? What do you think the number one solvent is? Water. Aqueous means it's specifically a water solution. And what does soluble mean? Yeah, be able to dissolve in something or be able to mix. And if we talk about sodium chloride is soluble in a aqueous solution, what would be your solute in that case? The sodium chloride. And what would be your solvent? Which is, now we know, water. Exactly. And so that's what we're going to be working on this unit as solutions. Most of them are going to be water solutions. And then there'll kind of be some calculations, of course, that go along with that. We wouldn't have our chemistry unit without calculations, although not today. We won't start. So actually, the part of the notes that we're doing today is all repeats. We've done all of this before. So we're not doing anything new today. So just refreshing your memory. All right, so we're going to start off with a closer look at water because water is considered the universal solvent. And a lot of what we covered today, talking about water, I think y'all covered back in biology too. So the water molecule is said to have a bent shape, which gives it bond angles of 104 degrees. We did that on molecular geometry. If you think about a water molecule, this oxygen has two lone pairs, so those lone pair repel the electrons that are in the bond, and so instead of being linear or just straight across, that kind of forces them to end up being bent. And it is polar, which means it has a slightly positive, slightly negative, and not a full charge like an ion. And that is because oxygen has a higher electronegativity than the hydrogens, and therefore attracts the electrons more strongly than the hydrogens. And that makes it polar. If you remember from periodic table trends, electronegativity is the ability to attract electrons when they're covalently bound. So if we look at a water molecule, we say that the side of the oxygen has a dipole that is slightly negative, and the hydrogens are slightly positive or have a dipole that is positive. And like I said, that's not a full charge. And the reason that is oxygen is a lot more electronegative, so it causes these shared electrons to kind of be shared unevenly and pull toward the oxygen. And that's why we get more of the negative side on the oxygen side and more of the positive side on the hydrogen side. And since the water molecule has a positive and a negative side, it is attracted to a wide variety of solutes. Anything that has a charge, the water molecule is going to be attracted to, and that's why it's considered the universal solvent. So if I have another water molecule, this other water molecule would line up where the oxygen is going to be by the hydrogen, because the hydrogen's positive, the oxygen is slightly negative, so opposites attract. Same thing, my next water molecule, if it lines up here, it wouldn't be a hydrogen because those would both be positive and they would repel. So it would line up once again, so the oxygen is going to be facing the hydrogen, and then you would have a hydrogen bond formed between the two. So in water, the IMF, or the intermolecular force, that's the force holding the water molecules together, comes from hydrogen bonding, which is the strongest, INF. And then the intramolecular bonds, which so that's an example of an oxygen holding the hydrogen together. Those are covalent, which means the electrons are being shared there. So I probably kind of jumped ahead. Water exhibits hydrogen bonding. And that exists when hydrogen is bonded to a highly electronegative atom like nitrogen, oxygen, or fluorine. And we have oxygen in this case. And it's attracted to the lone pairs of these atoms in the same or nearby molecules. And because of this hydrogen bonding, we have a lot of different properties that can be contributed to water. And that's all the listing right there. High surface tension, adhesion and cohesion. The density of ice becomes smaller. That's why ice floats in water. High melting and boiling points. We'll use that during this unit. Capillary action, low vapor pressure, which means it doesn't evaporate very quickly. High specific heats, we'll talk about that, and we'll also talk a lot about it being the universal solvent. If something has a high specific heat, that means it can resist changes in temperature. So like a swimming pool, for instance, it may be 110 degrees outside, but if you jump in the swimming pool, it's still going to feel relatively cool because that water has a high specific heat. It can resist changes in temperature. And all of these things make it good in our bodies. And like I said, also in chemistry, because we can dissolve a lot of things in it. All right. So when we talk about surface properties of water, surface tension is the inward force or pull that tends to minimize the surface area of a liquid. So that would be why water forms drops instead of always spilling out across the tabletop. If it gets too much, then you overcome those forces. But you can have a pretty good amount of water and you can spill it and it's going to go into a drop rather than spilling. That's what we're talking about, surface tension. So an example of this would be a drop of liquid having a spherical shape. Also, if you've ever seen insects that look like they can, or that look like they can walk across water, or they can stand on the top of water, and that's because water has surface tension, and they're so light that they can kind of stand on that surface. If you have a surfactant, that's any substance that interferes with the hydrogen bonding between the water molecules and reduces the surface tension. So if you have something that's dirty and you add soap to it, because soaps are surfactants, it'll interfere with that hydrogen bonding, and then it can go and surround that dirt particle and then cause it to be washed out whenever you start rinsing it. So example of these would be soaps and detergents. If you drink out of a glass, that does not look spelled right, but I think it is. If you drink out of just water out of a glass at home, you may just rinse it out because you probably don't have that many water molecules. But if you have something that's really dirty, you're going to use a detergent. Usually just rinsing it with water is not enough, and that's because you need to interfere with those hydrogen bonds. Capillary action is the ability of a narrow tube to draw a liquid upward against the force of gravity. So straws in a drink, or if you've ever been at the doctor, you've had maybe your finger pricked and then they get a really tiny glass tube and it draws that blood up. That's capillary action. And that's also due to hydrogen bonding. So, and we also would see capillaries in tree trunks. So the water can be taken from the ground all the way up. It could be a really tall tree, so very much against gravity. And that's because you're seeing a lot of cohesive properties with water, and that's where your H2O or water molecules stick to itself. And you're also seeing adhesive properties, which is when water sticks to or is attracted to something else. So for instance, the water could be attracted to the size of the capillary, and then they're also attracted to each other. So it kind of drags those molecules, those water molecules, up against gravity. All right. So the next one is vapor pressure, which may be one that you're not real familiar with. And we use it just kind of in one area of our notes here on solutions. So vapor pressure is the vapor pressure of water is low, because the tendency of water molecules to escape the surface of a liquid and enter into the gas phase is low because of the hydrogen bonding. So I can spill some water and I may come back days later and that water may still be there, especially if it's inside your house where it's pretty cool. On the other hand, something like gasoline, if I spill gasoline, it's volatile, which means it has a high vapor pressure. So it's going to evaporate, especially if you have it outside. So the less volatile, which water is not volatile at all, volatile is how it evaporates or changes from a liquid to a solid, the less volatile, the lower the vapor pressure. Also, the density of ice, the fact that liquid water floats when it becomes ice or floats when it freezes, is due to hydrogen bonding also. When most compounds go from liquid to a solid, that usually makes them more dense and they usually end up sinking. So that's kind of another interesting property of water. Water also has a very high melting point, a high boiling point, and like we said earlier, high specific heat, and it is considered the universal solvent because it can dissolve so many things. And the picture just shows you an example of an ionic compound. So this is sodium chloride, but if you remember back from double replacement reactions where we had to use the solubility rules, it doesn't exist like that whenever we put it into an aqueous solution or we put it into water. It actually is going to separate into sodium ions and chloride ions. So positive and negative ions. And so if you have the chloride, the negative ion, the water is able to cause it to go into solution by surrounding it and lining up with your positive hydrogens against the negative chlorine, because we know opposites attract. But then it's still also able to handle the positive sodium. It's just going to kind of flip itself around, and now the negative oxygen will line itself up around those. And that's called the process of solvation, where water is able to surround something and kind of drag it into solution. All right, and we have actually had this page of notes before, this exact page of notes, so it's just really a refresher. So types of matter, so far we've been looking really the most at pure substances. And that's either going to be a compound or element. So a pure substance cannot be separated physically. So then we can separate it into elements, which is going to be straight off the periodic table. Those cannot be decomposed by a chemical means. And then if we combine, two or more elements, and we get a compound. And those can be broken back down into their original elements. So we're going to spend a little bit more on the other side of the flow chart when we're talking about mixtures. So mixtures can be physically separated. So even our salt water, if we boiled off the water, we would end up with our salt. So that's still considered physical means. So a homogeneous that should be an S. I don't know what I got going on there then. Has a uniform composition throughout. It's also called a solution, which is what our unit is about. So we're going to be dealing with those mainly, as compared to a heterogeneous mixture that does not have a uniform composition. So I think a trail mix kind of an obvious example. And under those, we have colloids and suspensions, which are going to be a little bit different of the two based off of their particle size. Does anybody remember those words, colloid? No, thanks for being honest. All right. All right. Okay. So let's move on down a little bit. All right. So solution, homogeneous mixture, those are the same thing. We're going to be calling it more solution during this unit. So that can be any substance, a solid, liquid, or gas that is evenly dispersed in another substance. That does not mean they chemically reacted. That just means it has dissolved. So saline solution, which is a salt solution, is kind of just a real broad example. They do not scatter light, so that is referring to the Tyndall effect. Tyndall effect, and the Tyndall effect means something does scatter. Oops, I cannot. Sometimes once I record it, I just like to play it for my other classes, but I can't stand to hear myself talk on the video, so I can't do that. I think it'd probably be inappropriate if I left the class while I played it. I might get in trouble. It does scatter light. So if the particles are large enough, the solute is large enough, then you're going to get the Tyndall effect. In a solution, they're small and they've completely dissolved, so you do not get that effect. So we got the solute and we have the solvent, and kind of referred to those on our journal today. So the solute is a substance that is dissolved. Usually they're in smaller amount, and the solvent is what does the dissolving. And it's usually the one that's there in the larger amount. So suspensions have the largest particle size, and that is so large that it will settle out unless the mixture is constantly being mixed. So if you think of that pink medicine you used to take when you were a kid and it was kept in the refrigerator, and when your parents got it out, they shook it up, that would be an example of that. Also, muddy water. Anything, if it stands there for a while, then it's going to settle out of solution, and it may scatter light. It may or may not. Then the other one under here comes my colloid. And both of those are heterogeneous mixtures. So my colloid, the particle size is intermediate. So smallest in my solution, largest in my suspension, and the colloid forms in between. So the particles do not settle out. So an example of that would be fog or shaving cream. Probably don't see those as much. They always have the Tyndall effects because the particles are always kind of floating around in the solvent. If you've ever taken the cough medicine over the counter, Delsum, it kind of feels real thick. That's a colloid. The medicine is surrounded by some sugar and it stays in suspension. So if you could use the Tyndall effect to tell the difference between a colloid, I have there's really some kind of group text going here with my family. A colloid is always going to have the Tyndall effect. A solution would never have it. So that's one way you could tell the difference between the two. All right. So when we talk about our colloid, the dispersed phase is the colloid, can't say that, colloidal size particles, and then the dispersing medium would be the solvent. So colloids also do something that's called the Browning effect. Which is the movement of the solute, but it's, you can't just see it with your naked eye. You'd have to look under a microscope for that, but they're continually moving because they're not actually in solution, and they're also not at the bottom of the container. So colloids will stay dispersed because they form a layer of charge around themselves. So that's why they're able to stay dispersed. But then if you add something to them, like an ionic compound, then it's going to neutralize that charge, and then you would see the particles start collecting or start kind of grouping up together. All right. Yeah, I think the last thing is Tyndall effect on the bottom there, which I think I already covered. All right. And examples of colloids, we kind of already did that. So if you want to write jello and fog again, you can. Under examples, I think we also did that up here. All right, so we're going to talk about solvation, not salvation, but solvation, which is just a fancy word for the solution process. So solvation is a process by which a solute dissolves in a solvent. If something is miscible, M-I-S-C-I-B-L-E, then that means it is able to be dissolved in the solvent. So like sodium chloride is miscible in water. If it is immiscible, then it's going to be the opposite. It's not going to be able to dissolve. So the two, solute and solvent, are going to stay separate. So that would be an example of like, what dressing is that? French dressing? No, that doesn't sound right. What's that dressing that you have to shake up? Oh, Italian dressing. Sorry, my mind is having lapse. Italian dressing, not so much ranch, that stays in solution, but like Italian dressing, that's not going to mix together and stay together. Or oil and water, that would be immiscible. And our good old aqueous solution is when the solvent is water. So once again, we can go back to our saline or our salt solution. And that's what we'll be spending most of our time on this unit. All right. The little chart right there just shows you, gives you some examples of different types of solutions. You can have almost any combination. When you talk about phases, the only one you cannot have is a gas in a solid. So there's no way for a gas to be able to be dissolved in the solid. You can have a gas in a liquid. A Coke would be an example of that. Carbon dioxide gas pushed into that liquid. But you cannot get a gas into a solid. So when you talk about what will dissolve in what, we say like dissolves like, and this is in terms of polarity. So for example, water is polar, and so that means water will dissolve anything that is charged. And the different things that are charged are going to be our ions and polar molecules. So water, because it's polar, it can dissolve either of those. It cannot dissolve a non-polar molecule. That would be something like a fat, a fatty acid. If I put butter in water, that butter's not going to dissolve, and that's because it is non-polar. So polar and ionic were dissolving each other because they're both charged. polar and ionic will not dissolve nonpolar because these are charged and this is non-charged or neutral. And so I need to have something that is charged so it will be able to have the positive side attracted to the oxygen side of water and the negative side attracted to the hydrogen side. Nonpolar will only dissolve nonpolar. We don't do that nearly as much, but something has to be nonpolar before it'll dissolve something else that is nonpolar. All right, I think that is it on that, if I remember correctly. All right, when we talk about ionic molecules, and we'll do this in using our solubility rules again. So ionic molecules are the solute and water is the solvent. Remember that your ionic molecules, I really shouldn't say molecules because that says covalent. So your ionic particles will disassociate and that's how they become charged. And then the water will be able to surround them. So just like we did on that picture earlier, if I have sodium chloride, it disassociates into the positive sodium ion and the negative chloride ion. And then you have something charged, so you have a way for the water to come and surround it. If it is a polar covalent molecules, those do not ionize, but they have a positive side and a negative side or oppositely charged poles. So there's still something for the water to be attracted to. And then the last one would be if water cannot dissolve it. So that is if you have something that is non-polar covalent molecule. So that's going to be a lot of your organic molecules. Does anybody remember what organic means? Contains carbon. So a lot of those are non-polar, so a lot of times they don't dissolve in water. All right, factors affecting rate and solubility. We've actually already covered these earlier too. Where am I? What else? All right, so this is talking about rate, not amount. We'll talk about amount tomorrow. This is just talking about how fast something will go into solution. And there's a video, did I tell y'all there's videos to watch this week? So there's a video that'll talk about different types of solutions and solubility curves. And that's what we'll be looking at tomorrow. So the first way to increase the rate is by agitation or stirring. So that's why for making Kool-Aid, for making something where we're putting a powder in, we usually stir it up because it just causes it to go into solution quicker. So it's ready to drink. And the reason that is the particles, if you stir them, are constantly being moved. So that increases the interactions between the solute and the solvent. And so they go into solution quicker. And that's going to end up being the reason for all three of these, actually. If I crush something, or the next one would be crushing, then that increases the surface area of the solute. And once again, that allows the solute and solvent to come into contact with each other more, increases the rate they will dissolve. And then the last one is increasing the temperature. Last unit, we said that the temperature, Kelvin temperature specifically, but the temperature is a measure of the kinetic energy. So if I increase the temperature, I increase the kinetic energy. So once again, solute solvent particles are moving around more, and so they have an increased chance of coming in contact with each other. So all three of those in some way allow solvent and solute to interact more. And we've done these before. We said stir them, crush them, and heat them. Those are your three that increase the rate. So if you're looking at something like a sugar cube versus regular sugar versus powdered sugar, which I kind of think of this used more in baking, The powdered sugar has a lot more surface area, so it's gonna dissolve quicker than like something if you put a sugar cube in there. Alrighty, I think that is a good place to stop. And we'll pick up there tomorrow with a little bit of notes, and then we'll really spend more time on solubility curves. But you're not too hard. Right.